Hello, I'm Lauren, and I will be presenting the first half of this talk. My collaborator, Isabella, will be presenting the second half. We will be talking to you about formalizing interdisciplinary collaboration in the CogSci community. When it was founded, the cognitive science community sought to distinguish itself by its seamless integration and synthesis of ideas from a multitude of disciplines to study the mind's representations. In its original form, cognitive science spotlighted psychology, philosophy, linguistics, anthropology, neuroscience, and computer science. The aim to promote the exchange of ideas from multiple disciplines persists today, as demonstrated through the Cognitive Science Society's logo. However, a recent debate has provoked scientific introspection. Have we lived up to the promise of seamlessly integrating ideas from our foundational disciplines? We characterize the degree of integration as being more multidisciplinary. Individuals publish in more isolated groups, are more interdisciplinary, and individuals are more interconnected. We contribute to this ongoing debate by examining cognitive scientific co-authorship patterns over time. We ask three questions. 1. How interconnected are cognitive scientists' collaborations? 2. How separable are cognitive scientists' research topics? And 3. How does topic interest influence our likelihood for future collaboration? We address these questions using our dataset composed of papers and abstracts published in the Proceedings of the Cognitive Science Society's conference from 2000 to 2019. We also cross-compared with abstracts from the Vision Science Society. BSS focuses on a narrow research scope, and so we assumed it should have a more stable community structure. From the papers, we mapped out the co-authorship network of the communities for each year. We then asked, how interconnected are cognitive scientists' collaborations? Let's first briefly break down the components of a co-authorship network. Nodes represent authors, or the cognitive scientists that publish at CogSci in a given year. Edges between nodes indicate that the authors were co-authors on at least one paper together. This is an unweighted network. Edges were not weighted more if authors published more papers together. We can then examine how the co-authorship network changes over time, from 2000 to last year, 2019. While in 2000 we noticed that there are many small islands of authors, in 2019 there is one large island in which many authors are connected. We could then measure the size of this largest island, or the maximum subgraph, which provides evidence toward a more interconnected or disconnected collaboration structure. How do we interpret this metric? A proportion that is very close to 0 can reflect that authors are all publishing completely in isolation. Alternatively, as the proportion gets closer to 1, more authors are integrated in the core group, and hence there are fewer isolated islands of researchers. Over time, we see that the proportion for both CogSci and BSS are increasing, implying that authors from both communities are becoming more integrated. We asked, how interconnected are cognitive scientists' collaborations? And we found evidence that CogSci authors are becoming more interconnected. However, this is obviously not the full story. Authors are not just featureless nodes in a network. Rather, collaborations between authors are driven by authors' research topic interests. So we next examine the structure of the topic space. Authors may publish one or more papers with other co-authors. One bottom-up approach to tag semantic structure is to use topic modeling, a common out-of-the-box tool used in text mining. The topics can be inferred from the contents of the papers. A paper can then be represented by its distribution of topics, where some topics may be heavily featured in a paper, such as children development in this case. And within that same paper, some topics, such as communication, may not appear much at all. Of course, each paper is unique, so another paper, even when written by the same author, could have a different distribution of topics. We average over all papers published by each author in a given year to compute the author's distribution over all topics. In our analysis, we extracted 100 topics. Authors can be represented as a 100-dimensional vector. To analyze the integration between topics, we projected the topic space onto 2 dimensions. Here we have the topic space from CogSci 2000. For each year, we computed the clusters, providing a set number of clusters of 5 for each year. With a stable number of clusters across years, we could analyze the separability of authors' research topics and how it changes across years by measuring the tightness within cluster compared to the separation between clusters. Intuitively, tighter clusters that are more separable implies less integrated research topics. So on the y-axis, we have the ratio of total tightness within to total separation between. Values higher on this measure translates to clusters being less separable and more integrated, while values lower on the ratio translates to more separable clusters and thus less integrated. Over time, we see that VSS stays relatively stable, while CogSci rises, so clusters are becoming less separable and more integrated over time. This trend is also visible in the visuals of the clusters, comparing the earliest years to the most recent years. We asked, how separable are cognitive scientists' research topics? And we found that authors' research topics are becoming less separable. For the next section, I will hand it off to Isabella.
Thanks, Lauren. So far, we've looked at authors' connections and their topic interests, but interdisciplinarity does not depend only on network structure or authors' topic interests alone, but on the distribution of topic interests over the network. How does topic interest influence our likelihood for future collaboration? To answer this question, we need to combine network and topic measures. For this network, we can think of the colors as representing different topics of study. We can then ask whether connections are more likely between authors who study the same topic than between authors who study different topics. The question of interdisciplinarity then boils down to the similarity of topic interests within collaborations. In a more multidisciplinary network, we could expect collaborations to more often occur between authors with similar topic interests than between authors with different topic interests. Interdisciplinary networks, on the other hand, would have more collaborations that cross topic interests than within similar topic interests. Our measurement of topic interest is derived from topic modeling. This measurement is continuous, but we can still ask if similarity in topic interest predicts the likelihood of a connection between two authors. We treat each author's distribution over the 100 topics from topic modeling as a unit vector in a 100-dimensional space. This simple illustration with two topics shows the angle between two authors' vectors. We then measure topic similarity between authors as the cosine of this angle. To measure how topic similarity influences the likelihood of collaboration, we introduce a link prediction model that uses publications from year n to predict publications in year n+1 in a logistic regression. Since people who published together previously are more likely to publish together again, we use prior collaboration from the previous year as our first predictor. This will control for the strong order of correlation in collaboration network structure. We then use topic similarity between authors in the previous year as our second predictor. New collaborations are of particular interest. We want to know if similarity in topic interest is a significant predictor above and beyond the existence of a prior collaboration. This would suggest that topic interests play a role in the formation of new collaborations. We find that the formation of new collaborations is positively predicted by topic similarity. So a 1 standard deviation increase in topic similarity increases the odds of a new collaboration by 8.51. So a new collaboration between authors who have dissimilar topic interests would be less likely than a new collaboration between authors who have similar topic interests. We are also interested in what happens to prior collaborations in the following year. If authors collaborated before, what role does topic similarity play in their likelihood to collaborate again? This will tell us whether the importance of topic interests in collaboration structure is persistent across time. We find that repeated collaborations tend to cross topic areas. A 1 standard deviation increase in topic similarity decreases the odds of a repeated collaboration by 4.57. So repeated collaboration between authors with similar topic interests would be less likely than a repeated collaboration between authors with dissimilar topic interests. The interpretations depend on the validity of our link prediction model. To test our model, we use the data from 2019 to predict the collaborations we would expect to happen this year and check those predictions against the actual collaborations that happened in 2020. This matrix shows the full model's predictions for the 50 most central authors at CogSci in 2019, where a lighter color indicates a higher probability that the two authors will publish together in 2020. Here are the actual collaborations from 2020. We used a receiver operating characteristic, ROC analysis, to evaluate our model's predictions. ROCs can be used to evaluate a model's classification accuracy when the predictions are for a discrete variable, publication in our case, are probabilistic. Overall, our model performs well above chance with the area under the curve of 0.87. This is not particularly surprising because people who published together before are very likely to collaborate again. Of more interest is how our model fares when we remove the set of authors who collaborated together in the past and predict the new publications based solely on authors' topic similarity. When we predict new publications only, our predictions are still above chance with an area under the curve of 0.67. As you can see, the ROC curve is far removed from the dotted line, which represents at chance performance classification. This means that the above and beyond autocorrelation, topic similarity successfully predicts new collaborations. Our model was successful at predicting this out-of-sample 2020 data, even when we only consider new publications. We conclude that the link prediction framing is a valid tool for exploring the connection between topic interests and collaboration structure. Using this link prediction model, we found that the formation of new collaborations tends to be within the same topic interest, and that repeated collaborations tend to cross topic interests, suggesting that collaborations between authors with different topic interests is more persistent over time. In closing, we consider how our findings contribute to the ongoing debate. Is CogSci becoming more interdisciplinary? Our results are consistent with the field becoming more integrated across a range of measures. In other words, we provide evidence that authors are increasingly collaborative within an existing topic space. But integration of this sort is not the only aspect of interdisciplinarity. Other authors, notably Nunez et al., have raised the concern that the field has seen a decrease in diverse perspectives from other disciplines like anthropology. We note that the current results do not comment on the diversity of CogSci perspectives. Expanding the methods presented here with existing measures of diversity will better address the global changes in cognitive science research. Thank you for your attention, and we'd like to thank our co-authors Eric Brockbank and Ed Voll, and all the sources that help support this research.